No, I don't think so.
Right guys, good afternoon. I'm Dennis from Ancon over the water in Sheffield. We've come across, we've been invited across to just tell you a bit about our products. Not technically, not a salesy thing. So hopefully at the end of it you won't feel like you've had your arm twisted up your back to buy anything. So just a bit about to explain Ancon products and show you what's good for what and what's not good for what. And if you've got questions, just chuck them in as we go through. I've rehashed this seminar slightly, but to combine, make two CPDs combined, but you should be able to ask me questions without me getting thrown off my stride. I've got to start off with a little bit of corporate bollocks that our marketing people insist that I do, but it's not, again, it's not salesy, just about who we are. So Ancon, based in Sheffield, over in the UK. We have a factory in Sheffield which makes sort of the heavier stuff that we do, shelf angles and wind posts and things. We've got a factory in North Wales that chucks out 100 million wire wall ties every year, and then we've got various bits and pieces around the world, distributors and factories and outlets, mainly on the concrete products that we do, rather than the masonry products that we do. And that's it for that. That was easy, wasn't it? A lot of what we do in Ancon is made out of stainless steel, and because Sheffield is still the home of stainless steel in the UK. It's not made by a British company anymore, it's made by a company called Outokumpu, or actually a Finnish company who took over British Steel Stainless. But stainless steel is still made, all the stainless steel that's made in the UK is still made in Sheffield. And the reason we make things in stainless steel is that a lot of the stuff we sell goes into cavity walls, and when you put stuff into cavity walls, you can't maintain it, you can't keep monitoring it and checking it and putting another coat of paint on it or anything like that. So you need something that you can fit and forget about completely, and that's what you can do with stainless steel. And that's because it contains chrome. You need at least 10.5% chrome in stainless steel to classify it as stainless steel. And what happens is that as it's produced in Sheffield and it comes off the rolling mill, it comes off the rolling mill in a big continuous slab about the size width of this table and 100 metres long and 6 inches thick. And as it hits the atmosphere, the chromium molecules that are nearest to the surface of the steel in the steel react with the oxygen in the atmosphere and form a very, very thin layer of chromium oxide on the surface of the steel. So it's pretty much like putting a zinc oxide coating on with a paintbrush or in a galvanising bath, but it just comes as part of the manufacturing process. It's microscopically thin, this coating. It's about 3 angstroms in thickness. To give you an idea of how thin 3 angstroms is, if you imagine a 3mm thick piece of stainless steel plate, 3 angstroms on the top and bottom is the same as having a playing card on the top and bottom of a 10-storey building. So it's microscopically thin, it's really, really feeble, it comes off with your thumb as you're handling the stainless steel, but all that happens is, as the film gets removed and damaged in any way, if you cut through the stainless steel, or take a file to it, or drill a hole in it, or anything like that, all you do is you remove one surface, but you create a new surface underneath, and the chromium molecules next to the new surface that you create react with the oxygen again, and this chromium oxide layer just regenerates itself instantaneously. As long as there's oxygen there, you've got a self-repairing material, which means that you can put it in, forget all about it, you don't have to maintain it. And that's why basically your knives and forks and things don't go rusty when you're chucking them about in the drawer and then washing them and chucking them back in the drawer and things like this. Now, there are a number of grades of stainless steel. We keep getting this really boring email from one of our directors who thinks it's really funny because it's called 50 Shades of Stainless Steel. And every week we get a new shade of stainless steel because there's loads and loads of different types of stainless. But only 2 or 3 types get used in construction really. The one that gets used overwhelmingly is grade 304 stainless steel. Nowadays it's known as 14301 because we all live in Europe. We have to have a European, we have to have a German number for everything actually. It's a German number there. And it used to be called 188 because it's got 18% chrome, much more than the 10.5% minimum, and 8% nickel. What the nickel does is it makes the steel tough and ductile, and that means we can bend it and shape it and form it and weld it and cut it and all the things that you need to do if you're using stainless steel in construction. That is very, very resilient, and for 99% of the applications that you'll ever come across, particularly in cavity wall construction, grade 304 is what you're going to be using. All of our stuff comes as standard in grade 304, and we only upgrade that if we specifically need to. What we'd upgrade it to is grade 316, which has the same amount of chrome, a bit more nickel, and 2% molybdenum added to it. And the molybdenum is the magic ingredient that makes this even more durable than the grade 304 stainless steel. This sort of stuff goes into roads and bridges applications where people want things that are going to last for 125 years. They design design life of a dowel in a highways application, something like that. So 316 is used for that, and things that you want to stay nice and shiny for a very long time. So the flashings on the Lloyd's building in London, Canary Wharf Tower, anything that's shiny stainless steel that you want to stay shiny, you'd use 316. And that's because the 2% molybdenum gives it an added resistance to pitting corrosion, which is what stainless steel can suffer from. If dirt gets on the surface of the steel and deprives it of oxygen so it can't self-repair, you can get little pockmarks of rust which will eat their way. It's not conventional rust, it's corrosion which can eat their way through the stainless steel. And the 2% molybdenum actually helps to guard against that. I've just found out this morning that I also had a bit of a guess, but I found out this morning officially that the difference in price between 304 and 316 is 48%. So you do need to only use 316 when you need to. We did have an architect once who on the Churchill Centre, shopping centre in Brighton, decided it would be a really good idea to have all the wall ties and all the restraint fixings in grade 304, except the side that faced the English Channel, where he made everything 316. Unfortunately, you can't tell the difference between them without doing a spark test in a laboratory. So all the wall ties came to site, got tipped into a big vat, and nobody knew what was going in. So if you're going to use 316, use it throughout your job, but as I said, don't use it unless you really feel you have to. And it is really for aggressive environments. If you're building something in the Liffey where water's going to come up and cover it and then go down again at low tide, you'll want 316. If you're building something that's getting built into a wall next to the Liffey, then 304 will do it. Now the stuff that we make out of this magic material are these things. Wall ties and restraint fixings are designed to tie the two skins of your masonry together. Most masonry construction, or most wall construction in the British Isles consists of two skins. So you've got block and brick, or Methsex studs and brick, or timber and brick, something like that, or block and block, with a gap in between. So you've got two leaves of masonry. And the wall ties and restraint fixings tie the two leaves together, so they work compositely, and tie the edges of the masonry panels back to the structure, so they actually make your wall stand up. Wind posts and masonry reinforcement are just bits of secondary steel to get your walls to stand up under wind loading. So if you've got a big long wall panel and a high wind load, if you're spanning 9 metres between columns, you might struggle to get your wall to work. So you'll put in a wind post, or you'll reinforce the masonry with bed joint reinforcement. Brickwork support systems, I'm telling you things you already know, I'm sure, but brickwork support systems are basically a shelf angle that you fix to a floor slab, and they traditionally go into multi-storey buildings. You're not allowed to build buildings from top to bottom for the height of Dublin Castle or something like that. You've got to break them up into panels, and obviously when you put a horizontal squashy joint into some masonry, you need to sit the brickwork above that onto something fixed back to the structure, and that's where a masonry support system is. And lastly, we also make stonework supports and restraints, which I'm not going to cover in this CPD because I'll have to trim it down a little bit. But stonework supports and restraints are exactly the same as these, except they're designed for stone rather than for brick and block. So I'm going to go through these sort of areas and just highlight what's good, what's bad, what you should use where, what you should try to avoid. And if you have questions on cost, because I noticed there was a few people like QS after their name on the list distributionist, these lads are the people you need to ask cost. I work in technical department and I always get asked, so how much does that cost? And I can honestly, hand on heart, say, most of the time say, I don't know, I only deal with the kilonewtons, not the pounds, shillings and pence. So, should also say, before we quite process, everything that we do now has a CE mark. Since last July, everything that could have a CE mark has got to have a CE mark. And it's actually illegal for us to sell things that aren't CE mark if there could be. CE marking is required when you've got a component that has a uniform means of testing adopted throughout Europe. So if we make something and the whole of Europe tests it in a specific way, we've got to get it tested and get it stamped with a CE approval to show that we can sell it in the European Union. The only things that we can't do are things that we fabricate on a bespoke basis. So if we're doing a masonry support system for a building in Dublin, and it's all designed to suit that particular building, there's no way of testing it. So in that instance, our fabrications, all our CE approval comes from the fact that all of our designs and all of our fabrication methods and all of our internal sort of applications in the office, the way we work, are all done to approved European standards, and that's how we get CE approval for that. So CE marking is something we've adopted. I don't know whether our competitors have, I would like to say, but I suspect they have as well. So, the thing that we make most of at Ancon is the humble wall tie, a deadly boring component. Nobody wants to talk about it. When I'm seeing architects and engineers on live jobs, we talk about wind posts and shelf handles and things. Nobody ever wants to talk about the wall ties. The engineer will say, you can specify them from a book, so I'll leave that to the architect, who just has to look in a book and pick a number, and the architect will say, I employ structural engineers to specify things like this because that's a structural element. So nobody wants to talk about them, but they're absolutely vital. They tie the two skins of masonry together so it doesn't fall over. They hold the insulation against the inner leaf to keep the building warm, and they have a drip in them to make sure that any water that gets through the brickwork drips off into the open cavity. So the wall tie actually makes your building stable, warm and dry. So it's an absolutely essential piece of kit. As I say, we make about 100 million, 80 to 100 million wall ties every year. Even in 2008, when the world was going to end and financial institutions were closing down, people were walking off building sites and dropping themselves off bridges and things, and we thought we'd make 8 to 10 wall ties. I think we still made 70 million wall ties. God knows where they all go. I think most of them just get ploughed into the ground on a building site somewhere. I think Longs have quite a few of them in stock, to be honest, which we'd like to pass on to you, obviously. So, wall ties, although they're boring, are very complicated. They're probably the most complicated thing that we do. There are more rules and regulations governing wall ties than almost anything else that we do, most of which seem to have been made up over a few pints of Guinness in a pub somewhere, because they don't seem to make a lot of sense. But with wall ties, what you do is you put them in your masonry on a block by block basis of every other block in 2 directions. So the space at 450 vertically, 900 horizontally. You usually stagger them so you get a sort of checkerboard pattern. And adjacent to windows and doors, you stack a row of ties up within 1 brick of the edge there. And the rule is that they can be at 300mm vertical centres. But if you've got blockwork on the inside, that generally turns out to be 225, so that you can get it into the block joints. Unless you're using, as they do in Ireland quite a lot, I understand, blocks laid on the side, laid flat, going up. So in that case, you would be at 300 if you've got 300mm blocks laid flat on the side. Around the edges of the panels, we would tie the frames back to the masonry panel back to the structural frame using special ties, which I'll show you in a moment. But for the time being, we just look at the standard cavity wall ties, which are quite complicated. You would think that if you're tying 2 leaves of masonry together, somebody would just come up with a bit of steel that ties the 2 leaves together, and that's job done. And that is essentially what happens with a type 1 wall tie. You have different strength categories for wall ties. Type 1 wall ties can be used anywhere. It doesn't matter how high your building is, it doesn't matter if you're building on the top of a cliff, in the bottom of a valley, anywhere at all, you can use a type 1 wall tie. The only limit would be the cavity that you're working across, because our standard wall ties, obviously as manufacturers, we have to decide what is a sensible cavity. We could make all of our wall ties that would work across a cavity the width of this room, but they'd be the size of an RSJ and nobody would buy any, so we have to guess. And currently, we guess at a 175mm cavity. So all of our ties will work across a 175mm cavity. The ST1 is cheap, very cheap for a type 1 wall tie, because it's made out of very thin material but profiled like a little beam. So although it's cost effective, it's not as cost effective as these cheap and cheerful wire wall ties. So that you can use anywhere, but in most instances it would be over specified. In the centre of Dublin you wouldn't need anything like that unless your building was more than 5 metres high, 15 metres high. You'd get away with an RT2 wire wall tie. The rules for type 2 wall ties are that you can use them as long as your building's not more than 15 metres high, and as long as the altitude of the site is not more than 150 metres above sea level. And that's what I said about these rules being a bit arbitrary and a bit weird, because we do jobs in places like Halifax, which is quite hilly. Last of the summer wine country, for those of you who don't know where Halifax is. Last of the summer wine country, and we'll get 2 buildings side by side on the same site. One will be 149 metres above sea level, so we'll use these wall ties. The next building up will be 2 metres higher up the road, so we've got to use these wall ties, which seems absolutely nonsense to me. We don't actually do that. What we do is we put more of these wall ties in to compensate by putting more ties in, few weaker wall ties. So that's a type 2 wall tie. There is a type 3, but nobody uses it particularly because it has a wind speed limitation on it, as well as the height of building, and the wind speed limitation limits the use of the tie to certain geographical areas, and nobody's really come up with a business plan for why we should make a wall tie that we can only sell in Kent. So nobody really makes type 3 wall ties. We do make type 4 wall ties. Type 4 wall ties are exactly the same as these, except that the wire is thinner, and they're used in box form domestic dwellings only. This is a type of housing, which is what that means. That's housing wall tie. It's nothing to do with HRT treatment that ladies get when they get to 50-year-old or whatever. This is a housing wall tie there. It's a thin wire wall tie for use in houses or party walls in very, very high buildings. So if you've got a 25-storey tower block in the centre of Dublin, divided into separate properties, and you've got cavity walls between adjacent properties, this is the tie that you want to put in the cavity wall. Otherwise, if you put this tie in, there's a chance of too much sound being transmitted through the wall ties. And at least in the UK, building regs don't allow you to use that in a party wall. They might in Dublin, maybe you don't mind noisy neighbours in Dublin, I don't know, but I wouldn't think so. So these wall ties, these wire wall ties are very, very thin. This is 3.3 millimetres in diameter, this one. This is 2.5 millimetres in diameter, which means that architects can ignore these. When they're doing heat loss calculations for their building, they can ignore these ties because so little heat is transferred through the ties. They do have to consider the heat going through the ties with a type 1 wall tie, but as well as these, we also make what we call Teplo ties, which you might have come across. A Teplo tie is a round stick. It has the texture of a nail file, which actually is what gives it its embedment in the mortar. It's very, very light, and it's made out of basalt. It's made out of basalt fibre, which we actually get from Russia, set in a resin matrix. It's a very, very strong, very light wall tie, and has a thermal conductivity of only 0.7 watts per metre per degree Kelvin. So it's incredibly thermally efficient. And architects have taken to getting rid of these and putting these in instead, which is not a good idea really, because these are very cheap and they conduct very, very little heat. These conduct even less heat, but you're saving a large proportion of a tiny amount of heat and paying 10 times the price for your wall tie as a consequence. So these really come into their own, and you get big cavities rather than the standard cavity of less than 175 millimetres. Architects do consider these sometimes in the heat loss calculations because they ring me up and ask me what the diameters are. In fact, we've got so many phone calls at Ancon asking about diameters of wall ties that we now publish them in our literature. But I remember one architect ringing me up and saying, what's the diameter of your RT2 wall tie? And they change from time to time. We find a new wall tie supply, we do a bit of research and we shave off 0.1 of a millimetre and make another £40,000 a year or something like that. So I said, well, it's about 3.3 millimetres. And the architect says to me, can you be more precise? I said, yeah, it's 3.300 millimetres. So I would have thought 3.3 millimetres was close enough for him anyway. But so these wall ties really come into their own when you've got wide cavities. When you've got wide cavities, you need big wall ties because they're not just getting stretched, they're also getting compressed. So a big wall tie for a wide cavity, if it's built into an inner leaf of blockwork and projects out into fresh air, waiting for the bricklayer to come along and build bricks around it, what happens is, if you've got a cavity that's that wide, you build your tie into your mortar, into your blockwork 75 millimetres, it sticks out this far. Because it's sticking out a long way, it needs to be big and heavy and thick and wide. So before the mortar sets, the wall tie just sags a little bit. Then the brickie comes to build the brickwork, pushes the wall tie up and just breaks the bond in the mortar on the inside, and the wall tie doesn't actually connect the two walls together. So we make a tie, which we call our Ancon 2-part tie, so called because it comes in 2 parts, and that's why marketing people get paid shed loads more money than anybody else, because they spot things like that. How brilliant is that? The idea of a 2-part tie is they project out just far enough to accept a clip to hold the insulation against the inner leaf, and then you simply clip in a variable length outer section to suit the cavity as the brickwork comes on, so you're not bending ties and you don't get ties bending and sagging. So whether you're using a 2-part tie or a big heavy 1-part tie, you will need to look at the heat, or the architect will need to look at the heat going through these wall ties. And what we've discovered is that if you've got a 300mm cavity fully filled with insulation, about 20 mil of the insulation is just compensating for the heat that's going through the big wall ties. And that's where the Teplo ties come into their own. Because with a Teplo tie, they're very, very light. You can build them into the mortar, and they're so light they don't actually sag under their own weight. And you can actually get rid of some insulation. We reckon that if you substitute a 2-part tie for a Teplo tie in a 300mm cavity, you can make your walls 20mm thinner. And that might not sound like a big deal until we did a job in Chelsea about 3 or 4 years ago now, called Manresa Court, where The walls, the architect was over the moon when he found out he could make the walls 20 millimetres thinner, because all his rooms got a bit bigger, and the client could actually charge, I think it was an extra £85,000 a year rent for his building because he'd used the Teplo tile. So obviously he sort of recovered the money, any money he'd spent. And these, in fact, are quite cost-effective against a two-part tile or a single tile for a large cavity. So that's where your Teplo tiles come in large cavities where you've got lots of insulation and you don't want a lot of heat loss through the walls. Frequently, I don't know why it's so prevalent over here in Ireland, but frequently in the UK we have now a METSEC frame on the inside instead of blockwork. Because it's a dry trade, people can get things working quickly, you can get inside the building quickly, you're not waiting for blocks to set and have block there as well. So instead of the blockwork, you have a series of metal studs on the inside. The insulation is fixed to the metal studs. That creates a dry envelope, gets your building dry, people can get inside the building and start working. Unfortunately, when the brickwork comes along at some later stage, if you've not got our channel on the front, you need to identify where the studs are, cut a hole in the insulation, put a tie in the hole, screw it to the metal stud, then block up the hole in the insulation, which is a messy, difficult, time-consuming operation. So what we do now is we supply a channel. Rather than fix the insulation to the metal stud just with a tech screw and a washer, we supply a channel, and the channel actually clamps the insulation against the METSEC stud. The screws that go through have a gap in them so you can't over-tighten them and squash the insulation down. And then the brick ties are simply clipped into this channel as the brickwork comes along at some later stage. This gives a type 3 performance because the tie bends and the lips on the channel bends between fixings and the lips will tend to open out. You get a type 3 performance, which means that you can only use it in 15-metre high buildings where the wind speed is less than 26 metres per second. So what we do when we've got taller buildings is we compensate by putting extra ties in. So if you need a type 1 performance, as you would do for a high building or a building that's at a high altitude, you would need ties at 225 centres on every metal stud. But the ties aren't particularly expensive. You'd have a channel on every stud anyway, so that's not a big cost disadvantage. What it does sometimes do is affect the way that the architect treats his building architecturally. We did a job in London called Cross Harbour a few years ago, designed by Skidmore, Owings and Merrill, who do skyscrapers in New York. This was a 16-storey building in London Docklands, and they wanted to clad it with big panels of stone so it looked really classy. But the wall ties needed to be at 225mm vertical centres because the building was very tall. So the maximum height of stone they could have was 225mm, and the architect just said, well, it's going to look like blockwork, isn't it? So I might as well just make it in blockwork. So he just used polished block instead. And I think the upshot was effectively that he saved a load of money, and everybody was very, very happy about it. But that's one of the ways that the choice of a METSEC stud on the inside can influence the way the outside of the building looks.
What about fixing the channel to the...
Fixing the channel is just tech screw. We did.
I know that, but if you're going to increase the number of wall ties, but are you going to increase the number of screws?
No, the screws are also at 450. It's really what the difficulty is that it's a very, very thin channel, and at a 0.5 load, the lips on the front of the channel tend to deflect, and the tie moves a little bit too much. So by sharing the load between more ties, you can just keep within the limit of the movement of the wall tie. So the fixings are always 450. So if you were to get rid of the channel and fix wall ties individually to the METSEC stud, you'd have the same number of fixings to do. So it remains a sort of fairly cost-effective item. Now, when you've designed your masonry panel, the engineer will always want to design his masonry panel as being supported on 4 edges, because that makes his calcs really, really easy to do, and that's why engineers like that, like a nice, easy life. So what the engineer will do is he'll tie the channels, the ends of the brick panels to the steel columns or concrete columns using debonded wall ties, so that the masonry can move and expand and contract and have a squashy joint between his column and his blockwork. And he'll tie the head of the masonry panel back to the structure in the same way. But what he needs to do there is have something that will accommodate deflection of the head of the slab or the steel beam above the masonry. So rather than just having a wall tie projecting down with a debonding sleeve on the top of some masonry, you should really use it. You could do that. In theory, a wall tie projecting down into the head of head of a piece of blockwork like that will stop the wall from falling over. The difficulty is that bricklayers very rarely fill the perp joints with mortar. You get maybe a dab on the front and the back. These joints are always full of mortar, the perps aren't always full of mortar, so a tie hanging down there isn't necessarily bedded in mortar, and the wall can actually move before the tie will stop it from falling over. Even if you did make sure it was full of mortar, the debonding sleeve on a wall tie only allows 10 millimetres of movement. So if you get more than 10 millimetres of deflection, the tie is actually jamming in the end of the sleeve and into the masonry below. So proprietary head restraints are used more usually for the head, well, as far as we know they are, more usually for the head of a wall fixing back to a structure. The SAH sliding anchor that we've manufactured for years and years was the original head restraint. What it is a steel stem, 25 millimetres wide and 3 or 4 millimetres thick, and that projects down in the cavity, and the wall ties that attach to it simply slide onto it. There's a slot in the wall tie, you slide some wall ties on, the ties tie the wall back to the stem, and the stem is fixed back to the structure, so effectively the whole of the wall is tied back to the structure at the head of the panel. The difficulties with these things are that if they're not straight, as the beam deflects, then you can get the stem will simply jam in the wall ties. If the ties are on in the wrong orientation, and you don't, you've got to put the ties on first and then build your wall. So if you get to this level here, and you find that this tie or that tie should actually be pointed in the opposite direction, all you can do is take some more brickwork down, slide all the ties off, slide them back on in the right direction, and then build your last bit of masonry again. And critically, to get the published load out of these things, you need the top tie within 75 millimetres of the fixing to get a full 1 kilonewton load out of these things. And we often find that doesn't happen. We get asked for these at 1600 millimetres long. I was specifically asked for some of these, can you do them at 1600 millimetres long? And I says, why would we want to? It says, you only need 2 ties on, so if you come down 100 mil or something, and you've got 2 ties to a block, I said, you need 400 or 500 mil. He says, we have only got 2 ties on, but we've got 2 ties down here, and then we've got 1400 millimetres of steel sticking up to the underside of a beam, which means you've just got a flappy bit of steel flapping about, it takes no load whatsoever. So these aren't absolutely ideal, and they are the sort of thing that we would specify if the other things didn't work really. But luckily, we have other head restraints that'll do the job much more easily. Our FHR is 2 angles. One angle is pushed through from the outside of the masonry, the other angle is bolted to the slab through this angle, so the two pieces of angle need a single fixing. You put a squashy joint in there, and the clamping action of these angles stops the wall from falling over, but it allows the slab above or the beam above to deflect as much as it wants to. Another marketing code, I didn't really know until I looked closely why it's called an FHR, but it looks like a little letter F. If you take a look, it's a little letter F. So again, our marketing people have earned their crust there. I shouldn't skip them because we won, this is a little plug for Ancon, I suppose, we got the award for the best literature anywhere in the construction industry. And our marketing manager, Annabelle, had to go to Grosvenor House Hotel in London to get presented with this big glass plaque thing. And she got presented by Jonathan Ross's brother, right? And all the paparazzi turned up, and I'm sure they were photographing Annabelle because she's marginally more famous than Jonathan Ross's brother. But we got this award, sits in our house, so they're not really rubbish. The other head restraint that we manufacture, which is even more user-friendly and popular than this one, particularly because this, as you can see, is visible. If you've not got a ceiling in there, you will actually see this piece of kit. And sometimes the architect will say to me, do I need to fire protect that? And the answer is, if there's a chance of a fire, I suppose you do need to fire protect it. So that may need fire protection, may be visible. Our IHR is a thin channel bent to a right angle with a stem that slides into the top of the channel. That sits in the masonry, is completely hidden by the dab of mortar each side that I've talked about earlier. Laps underneath the top block, stops the top block from falling over, and will accept 50 millimetres of deflection of the slab or the steel beam above that. It goes in a block joints. It'll carry 1.5 kilonewtons, and this is the most popular head restraint that we do. The two are comparable in price, I'm told, very, very similar in price. Dan might know better than me, but that isn't dissimilar to that. But this has many, many advantages. It's available as a hammer-on fixing. We do a lot of hammer-on fixings now because bricklayers don't like to put the trowel down and start drilling holes in steelwork for screwing things. They're much better at laying bricks, and they do it very quickly and efficiently. So we have some hammer-on fixings where you simply knock a staple onto the edge of a beam and clip the head restraint into the staple. The difficulty with these is that they only work in one direction. If you knock them all on from that side and the wind blows that way, they all just push off the steel beam. So you need to alternate them, and they're more expensive than the conventional system, which is simply screwed to the underside of a slab or a wall. So this is the one to use. IHR stands for internal head restraint. Another marketing coup there, because this is designed for walls that are visible from both sides, so you can't see how they're standing up. Sometimes people refer to it as a 1HR, so if your architect says to you, you need some 1HRs, that's what it means. We did have a builder who rang us about 3 or 4 years ago and asked for 600 of our international head restraints. For some reason, he'd worked out that the I must stand for international. So we were made up, we were saying New York, Paris, Milan, and Rotherham and Doncaster, and things like that. Mainly Rotherham and Doncaster, actually internal head restraints, and that's the one that is used absolutely most commonly. Now, wind posts and parapet posts are things that the engineer will probably design in rather than the architect. Most of the times when I'm working with architects and they're asking me for specifications for wind posts, and I'll say, in your bill, in your specification, put Ancon wind post to engineer's specification or something like that. These don't have to be stainless steel. Most of the stuff I've talked about already needs to be in stainless steel because of constraints of the European standards. You can make wind posts out of anything, chewing gum or elastic or anything you want to, because they're not actually embedded into the outer skin of masonry. But what they are is a piece of secondary steel with no other function than to get the brickwork to stand up. They're not supporting the floor above, they'll span from floor to floor, they're not supporting the floor, they're just stopping the masonry from falling over. So a wind post would go from floor to floor. A parapet post, as the name suggests, cantilevers up from a roof and simply restrains a parapet running around the head of a building. If we put that underneath a window, it would be exactly the same component, but we would call it a spandrel post rather than a parapet post because it's in a spandrel panel there. And you can see an angle wind post going in there, built into the masonry between these two windows. Now, we make wind posts in stainless steel. We sometimes sell them in galvanised steel. We'll get frequently, architects and engineers will specify a 150 by 75 by 10 millimetre rolled steel angle by Ancon. It's not an Ancon product, but as long as we've got our name on a drawing, we're not really bothered, so we're quite happy with that. And we will sometimes supply in galvanised steel if there's a large stainless element to the package. We're not galvanisers and we're not galvanised steel people, but if there's a huge amount of stainless and a brickie wants 25 galvanised posts, then we'll say, okay, we'll do those as well, just to ease things along. And we do these in a number of different sections. We do channel sections and angle sections and flat plates. Channel sections are called either WP1s or WP2s, and the difference between the two is that a WP3 is a C-shape. It's an open-fronted C-shape. A WP1 has got lips on the front, so it's almost a closed box with a continuous slot running down the opposite face that you can see there. WP1s we can only make, they have a slight strength advantage over an open-fronted channel, but we can only make them in 2 sizes, so they rapidly run out of steam. They're the sort of things that go into porches. When some old lady is building a porch and she rings us up and she says, the building control man has said I need a wind post, and we just send it out to standard WP1 wind post just to restrain the end of an unrestrained piece of masonry or something like that. For most sort of design scenarios that we've got, a WP3 would go in, because with a WP3 we've got a vast range of sizes that we can manufacture. All we need is for that dimension to be bigger than that dimension, so we can get a tool in to bend this thing. If it's very long legs and a very narrow back, we can't get in with a tool to bend it. So as long as the web is bigger than the flanges, we can get in and bend these things. Now, these look ideal. They sit in the cavity, nobody knows they're there. You build your brickwork and your blockwork straight past them. You have slotted holes to accept ties, to tie the masonry to the post, and the post is tied back to the floor at the top and the bottom. So nobody knows they're there, and they look perfect. They're very easy, but they invariably form a cold bridge. They're invariably deeper than the insulation, so you've got steel coming from the warm side to the cold side, so the architect gets the EBGBs about that. And obviously, the depth of the post, which governs its resistance to bending, is limited by the width of the cavity. So if it's only narrow cavity, you can only fit in a spindly post, and you might need lots and lots of posts more than you would otherwise need. So we also do an angle section. And with an angle section, we have our long leg, which we build into the blockwork in a leaf. We lap the other leg round the corner and run it parallel in the cavity. In other respects, it's exactly the same, but you can run the insulation past the front of it, and you get a deeper, more structurally efficient section. So you probably need fewer wind posts if you're using WP2s than if you're using WP3s, unless you've got a big wide cavity where you can fit a wide channel in. So these have the advantage over those, except that you do get a vertical joint in your blockwork. Not usually a big deal unless it's something that's visible. We did a job in Leeds called Roundhay School where the architect wanted these so he didn't have vertical joints in his blockwork. The engineer had specified these, and the poor old architect only found out about it at a site meeting. Last minute, when they're just about to start work on site, he discovered that he was going to get a vertical joint in his blockwork in this gymnasium every 2.5 metres, and he wasn't happy at money at all. And we looked at lots and lots of options, but in the end we couldn't get anything to work as well as these, and he just had to bite the bullet and put the wind post in, so he lives with the vertical joints. Apparently the lads in Leeds, because they're very pretentious, they don't like it and they refuse to do five-a-side and things like that because it doesn't look, the blockwork doesn't look very good. So but that's what they like in Leeds, and they're pretentious at that. Channels may have an advantage in a couple of instances. If you try to reinforce and strengthen a narrow pier between two windows and you put an angle in the middle of the pier, what you'll end up with is little slivers of blockwork stacked up either side of an angle. And if the blockwork isn't substantial enough, then it's too close to the edge. It doesn't contribute to the design of the masonry panel. What the engineer likes to do in that instance is frame the little panel between the windows with an angle. So you sit an angle on each side and build the blockwork between two angles. It's completely stable, he sleeps easy on a night, everybody's happy. Except that when they try to span a lintel over the window, they try to sit it on the masonry, and lo and behold it hits a post before it can actually get on the masonry. And we love that because we then have to make little H-frames where we incorporate two posts and a lintel, and there's all adjustment to be made and it gets horribly expensive, but nobody else likes it except Ancon, obviously. So in narrow piers, use a small channel and set it in 150 millimetres from the edge of the opening so that you can just sit the lintel onto the masonry before it hits the post. That's usually a more effective way of doing it. A channel is also ideal in a parapet situation. There's no cold bridging problem, the parapet would be uninsulated, and if you use an angle in there, you'll get a vertical, you'll be building the angle into that joint there, and you'll get a vertical joint in an external skin of masonry, which has got to be waterproofed and masticed. And it's difficult enough getting a DPM across here if you've got to cut it round a wind post. Better, we all say, to get the DPM down below there, so that you're not having to do origami and fit it around a convoluted chalice shape and seal it and gobble it up and everything. If it was a spandrel panel underneath the window, then I'd say use an angle, and then you can run the insulation past the front of it and you're not getting the cold bridge. But for a parapet, a channel section is ideal. Just look out for this, one thing to look out for. If you look in our catalogue, you will find that even the spindliest parapet post will take a considerable load because it's not spanning very high, it's only this high, it's a piece of steel, take quite a load. Engineers have been known to use our load tables and the wind loading that we've got and determine that the parapet posts only need to be at 5 metre centres. So the parapet's post is spaced at 5 metre centres, they check their masonry, that'll span 5 metres, everybody's happy, everybody tenders for the job, we give a price out for 54 wind posts. Then somebody wins the job, says John Sisk, win the job, come back to us and say, we want to buy these wind posts now, will you design them and detail them for us? And when we start designing them, we find out the post will take 5 kilonewtons or whatever, but the connection at the bottom to the beam and block floor, or hollow planks or timber or whatever, will take about half a kilonewton. So suddenly, you've got to have 5 times as many wind posts as you thought you were going to have, and the strength of the wind post and the strength of the masonry is irrelevant. It's this bit that determines how many posts you need. So when you're tendering, probably just get us to check initially to look at the bottom connection and make sure that the engineer hasn't underspec'd the wind post in terms of quantities. And that it applies exactly the same to an angle post in a spandrel situation like that. Now, masonry reinforcement can get rid of wind posts, not always, but sometimes it can. Masonry reinforcement is basically, as you well know, tram lines of steel laid into the bed joints of the masonry, either at 225 or 450 centres in one leaf or in both leaves. And what that will do is it will make your panel stronger so that it can span further between columns, get rid of wind posts. It will give it a greater resistance to wind loading, so if you're in a very, very high wind load situation, you can maybe get it to work with masonry reinforcement. And it can also stretch the distance between movement joints in masonry by about 20%. If a masonry panel is reinforced, then the movement joints can be spaced slightly wider apart. These are probably more considerations for the architect and engineer than for yourselves, but what you should know is that we now do masonry reinforcement in a lot of sizes. We used to do one size of wire, and just try and convince everybody that they didn't really need the wire that had been specified. We could use ours and it would be exactly the same. Now we go from 3mm wires to 5mm wires in 0.5mm increments, and we flatten down everything except the thinnest wire so that it's oval in shape, so that it's never more than 3mm thick. And that means that when you overlap two lengths of reinforcement in a joint, you don't get more than 6mm of steel in a 10mm joint, which is what you're allowed. We also do now, at the insistence of Carillion, who have some brick experts who get really hung up about minutiae of things, we now do something called XM, which has a little profile crossbar instead of a straight bar, so that the wires actually sit dead central in the 10mm joint. They don't lay on the brick at the bottom, they don't sit on the mortar at the top, they're actually in the middle of the mortar. Whether that makes a big difference, I really don't know, but that's what we do. And we do offer a design service now for masonry panel design. We will run a masonry panel through our software and determine whether it needs to be reinforced or whether it needs a wind post or whether it needs both in some instances. What we don't do is, although architects do try to get us to do this, is we don't take big boxes of drawings. We do get architects who just send us a big box of drawings or a CD of drawings and say, that's my building, design all my walls for me. And we say, no, we're not going to do that. What we need you to do is pick out the bits that you're worried about, give us a little profile like that, tell us what the supports are, where the openings are, tell us what the block is, tell us what the mortar is, and then we will run it through and see what it needs. What we usually get are panels that don't work, because engineers are very proud people. They don't want to get us involved. And the only time they send us one is when they cannot get anything to work, and then they'll send it to us and say, maybe Ancon can do something. And we've got exactly the same software as they have. We probably design fewer masonry panels than them, and we send back to them and say, we can't get it to work either, so you're going to have some wind posts in there, without a doubt. Now when we've got buildings like this one, and when I say buildings like this one, I mean tall buildings, I don't mean ugly buildings. We seem to have an aversion for photographing nice buildings that we've worked on. This is the city in Leeds. I hope to God John Sisk didn't do it. I have felt bad. I used to have a picture of a horrible building in Birmingham, and I always made the same joke about it. And it came up one day when I was doing a CPD in Birmingham at this architect's practice, and they all started muttering, and I thought, oh no, they've designed this horrible building. So I didn't make the joke on that day. When you've got a building like this, you'll have not only masonry reinforcement possibly, and all the restraint fixings, the wall ties I talked about, but you'll also have masonry support systems. Any building like this will have a masonry support system, because you're not allowed to just start building from the ground and keep building until you get to the top of the building, unless the building is less than 12 metres in height. You're allowed to build 12 metres of masonry uninterrupted in one lift from top to bottom, or 5 stories, 4 stories actually. A 5-storey building requires a movement joint. So anything that's less than 4 stories or less than 12 metres can be built in one lift. If you get higher than that, then you need to break up the masonry horizontally in exactly the same way as you need to break up the masonry vertically. You've got a vertical movement joint every 12 to 15 metres, and in a tall building you also need horizontal movement joints. The rule is that you can have 9 metres or 3 stories between movement joints. That's not always a good idea. Every time you put a movement joint in, you've got to support the brickwork above it on a shelf angle fixed back to the structure, so that you're not laying bricks onto some compressible filler, which is just going to squeeze out. If you've got, imagine, 9 metres of masonry coming up to an angle there, then you've got another 9 metres of masonry sitting on that angle, then you'll get shortening of the concrete frame as it dries out and shortens. You'll get deflection of the frame, and you also get deflection of the angle, and you'll get expansion of the brickwork as it gets warm. And all these combined deflections and movements mean that you have to accommodate a lot of vertical differential movement at this joint. And if you've got 9 metres below and 9 metres above, you're going to end up with a mastic joint, because mastic will only compress an absolute maximum of 50% of its original thickness. So you'll end up with a mastic joint running around your building, which is about 20 to 25 millimetres thick. And architects hate that. So generally what will happen is, although you lads might want to put, you might want to put the movement joint every 3rd floor, you probably get pressured to put them in every other floor if it's a domestic sort of residential development where you've got a 2,850 height. And if you've got a retail development where this is 4 metres or something, you'll probably have a masonry support system at every floor. So 1 or 2 floors, about 6 metres is the maximum that we like to go to, although we do have to exceed that in many instances. Masonry support systems come in a variety of forms. In the old days, when cavities used to be very small, when my house was built, I've got a 50mm cavity in the brickwork in my house, and I think most of the buildings at that sort of time had that sort of thing. A 50mm cavity, we would simply bend an angle, so we would take a piece of plate, bend it at a right angle, build the brickwork on it, and have the squashy soft joint underneath so that this brickwork can expand and contract underneath there. That's fine for cavities up to about 50mm, and we would still do that. And it's what we call a CFA, which stands for cold formed angle, because it's an angle made out of bending a plate. Most cavities these days are 150mm rather than 50mm, and what we do in that instance is, rather than just extend the leg of that angle backwards to the structure, which means the leg gets very long and ends up being very thick and very expensive, we push the angle that way, so it's hard up against the back of the brickwork, and then we span the gap from the angle to the structure with a series of welded channel brackets which go on at intervals depending on the load that we carry in and what we're fixing back to, of between 200mm and 500mm. And very occasionally we will actually use individual brick support brackets where we have a short length of angle and 1 channel bracket, and we position these at the end of every brick, so every brick spans between 2 individual supports. That looks horrible and looks very expensive, but it's actually quite cost effective in many instances. Well, in the one specific instance where you use it is when you've got brickwork curved on plan like that. The brickwork carved on plan gives us all sorts of difficulties. We've got to get an angle. If we use this sort of system, which we can, we've got to get the angle curved to a radius. And that's great, we can do that, but the angle generally needs to be thicker than it would otherwise be. If it's less than 6mm and you start to put it in a rolling machine, it tends to tear the angle and damage the angle. So these need to be at least 6mm thick when they'd otherwise be 4 or 5. It adds about a week onto delivery. It more than doubles the cost of the angle, and the tolerances never match up, because the brickwork tolerance might be on the architect's drawing plus or minus 7mm or something like that, and we will roll our angle to that. The concrete tolerance might be designed at plus or minus 15, end with plus or minus 25, so the angle doesn't always fit onto the concrete as nicely as we expect it to. With this sort of system, although you've got more fixings, you get rid of lumps of angle in between, there's no radius in, and it makes a more sensible, cost-effective detail if you've got tightly curved brickwork on plan, sort of turrets. If the brickwork is very gradually curved, anything less than 25mm radius, we just make this in short sections, say 700mm, and just facet them around the curve like an English 50p piece, that sort of thing. So that's how we would deal with curved brickwork. The detail of a masonry support system is generally that you put the bracket, the channels at the bottom of the slab, run a DPM over the top like that to stop any moisture from getting onto there and getting back into the structure, and tie the masonry back within 4 courses of the angle to stop the brickwork rotating around the angle as the bricks are being laid. And that, if you make sure they're in at 450 centres, you'll end up with a nice vertical brick wall sitting on the angle, so without any difficulty really. We provide thermal shims these days for many situations. The building research establishment came up with an idealised heat loss that they would like to see through a slab edge detail. In most instances we can achieve that without any difficulty, but if there's a very, very high load on the angle and the brackets are hanging down low below the structure or something like that, we'll need big brackets at close centres, so you've got quite a lot of steel penetrating the insulation, and in those sort of instances it's a good idea just to put a thermal shim in. It's just a 3mm thick, high density thermal packer which just gets the heat loss back to what the BRE would like to see. We can fix the steelwork rather than to concrete, or we would ask is that we get involved early doors to make sure anything that needs to be welded in the steel beam is in approximately the right positions so that they can work to it. We put a horizontal slot in the steelwork like that. We have a vertical slot allowing vertical adjustment, and a horizontal slot means that plates welded into a beam in Dublin will actually match up with bracket positions welded onto an angle in Sheffield. So if you've got slightly two directions, you've got a chance of the fixings matching up, which you wouldn't have if you had a round hole. You do need a round hole if you're fixing a masonry support system to a box section using an expanding anchor, a steel grip bolt. So in that sort of situation, what we say is offer the masonry support up at site, mark the hole positions and drill them at site, because you've effectively got no tolerance really if you're matching up a round hole with a vertical slot. And lastly, on this sort of bit of topic, we can suspend things underneath our angles if need be. Architects these days don't want to look up at the bottom of a window and see a steel lintel going across the top of the window anymore. And a lot of construction now, particularly in London, is designed as if it was to look like it was built at the same time as the Tower of London. So you're supposed to look at these buildings and see big deep walls, and it's all just smoke and mirrors. What we actually have is brick soffits hung underneath things. We used to hang these bricks, solid bricks, on bits of wire with rods going through the bricks and drilling bricks for dowels and things. What we tend to do now is cast brick, profile brick slips into a piece of concrete and bolt a brick-faced piece of concrete to the underside of our system to create the illusion of a big brick soffit. We can do the same with sort of etched precast. In that situation there, we've got large window opening here. This precast is too heavy and too long to span across the window as an opening. It comes in sections, so it has to be supported from above. So all of these are bolted to the underside of our angle, and the soft squashy joint is actually underneath there between the brickwork and the precast, which actually hangs off the structure at the top there. Now, one of the limitations of a masonry support system is that it's all building specific. We've got to draw it out, reference all the angles, do little plans like that, do different sections to show where things change. So when it comes to site for you guys to fit, or your lads to fit, it'll come as a big pile of steel, like a jigsaw puzzle. And there's always a piece missing as well, just there. And then it comes a big jigsaw puzzle with a drawing like that, so they pick out the right angle, put it in the right place in the masonry. All of this drawing and approval and manufacture and jiggery poking, getting it out to Ireland, means it takes about 3 to 4 weeks from getting an order to getting some angles to site. And every time I come to Dublin, where I used to come before, when Dublin was really bouncing, I used to be over here every week like I am in London now, and I'd get picked up from the airport, and invariably somebody would ring the second we got in the car and say, I want some masonry support. And the lad who used to pick me up said, when do you want it? I want it yesterday. And I said, no, it's 3 weeks, I'm afraid. So we developed a system that you can actually have yesterday. And we developed it in an Indian restaurant in Limerick one night. There was 3 of us, and we thought, this is nonsense. And we sat in this Indian restaurant and we knocked up an idea for what ultimately became our Ancon Optima system, where we have a standard off-the-shelf masonry support system that can be had on a day's notice